I've added this video in order to try and avoid some confusion when it comes to working out the exponent value. Now we said that whenever we're multiplying two numbers together we have to add the exponents. And we've seen in the last video that in order to add the exponents we take the exponent for the value x. Now this large ex, this is the actual exponent that's in the 32-bit floating point number, so it's the 8-bit exponent. Now this is the biased exponent. Now it's the biased exponent because it's already been biased. It's already had a number of 127 added onto it at some point previous. Now in order to add the exponents together we have to get access to the actual exponent. So we get access to the actual exponent by taking away the bias. Now the bias is 127. Now it's not minus 127, it is plus 127. And we're going to be adding and subtracting the value of 127. So don't get confused and start looking at the bias and say the bias is minus 127, therefore I'm going to have to subtract off the negative 127, therefore adding it. That's just to creating confusion. The bias is 127 and we add and subtract factors of 127. So we got this value here, which is the bias value minus 127. That gives us access to the unbiased value. So the unbiased value we'll actually call small ex. Okay, so this whole thing is the unbiased value small ex. Now we do the same thing for the ey. We take away the 127 and we get access to the small ey. And then finally, once we've added the two unbiased numbers together, we therefore have to bias it again by adding on the 127. So we add on the 127 here. And we've also seen that in the normal times the normal, we may have to add on a value of 1 or 0 depending on whether we have to normalize the result. So we've seen that in the last video and we got this answer here, and this is how you actually work out the exponent values. That's how you work out the new biased exponent value, meaning the actual number that you put into the 8-bit exponent in your floating point number. So it means that we can relate the small ex with the big Ex via these equations. So the big Ex, that is the biased exponent, if we subtract off the 127 we get small ex, which is the unbiased, and the same for the y. So that means that we could rewrite this equation here as, well, if we look at the top one here, this one here is just the small ex, this one here is the small ey, and we've got the 127 and we've got our 0 and our 1. So it means that it's slightly different. This one here says that we take the ex plus ey plus the 127, that's the bias, and this one is ex plus ey minus the 127. Now whenever I'm working through my workings on my program in Excel VBA, I'll be using the second option here. So I'll be actually looking at the unbiased exponent values because those are the values that we're interested to get access to. So let's run this up in the multiplication tool and we'll look at these large ex and small ex and large ey small ey, just to make sure that you understand where they are and you're not at all confused by it. So I've run up the tool here. Let's put a couple of numbers in. Let's put in 5 and 50. I'll move this out of the way because we're interested in the exponent values, and we've got the exponent values here. So we start off here with our exponent value for x. Now this is the 129 and this is the biased exponent. So this is the actual number here. So this is our x value and it's a 129. And then we take away the bias, which is 127, and it gives us our small xe. Now this small xe is the unbiased exponent and it's got a value of 2. Now we do the same for y. We've got the large ye, which is this number here, which is the biased exponent, and it's 132, and we take away the bias 127 and it gives us our small ye, which is the unbiased exponent. So in order to find the true exponent value, we're going to, after multiplication, we have to add these two together. So we're adding the 5 and the 2, and it gives us a 7. Now in order to get the biased value back, we're going to have to add the 127 back on, and this will give us our final biased output. So this will be the final output that we actually get in our floating point number. So this is our 8-bit exponent and our floating point number. And of course we can add on this extra 1 or 0 depending on whether it's normalised. In this particular instance, the first number up here is a value of 1, so it's already normalised, so it's a value of 0. So you can see then how we get the final answer here. We can get it in two ways. We can actually look at the unbiased values, which is our small xe and our small ye. So we're adding a small xe and a small ye, and we're adding on the 127, and it gives us our final result. The other option, which was the first one that we looked at, was looking at the output in terms of the original biased exponent. So we looked at 132 minus 127 and 129 minus 127, and when we added both of those together and we subtracted off the 127 here. So the two different ways of looking at it just depends on whether you look at it in terms of the biased exponent here or in terms of the unbiased exponent. So as I said, that most of the stuff we'll be working through will be in terms of this unbiased exponent, because that's what we want to get access to. So I hope this hasn't added any more confusion, and it's maybe helped to clarify a few things. So thank you for listening. I'll get you on the next video. Goodbye.